Assalamualaikum warahmatullahi wabarakatuh. Our group is doing electric scalar potential point charge. My name is Muhammad Hazizahan bin Muhammad Anafiah. My number metric is B0118101125.
Assalamualaikum and greetings. My name is Rajizul Ikmal bin Rajiz Zuhairi. My metric number is B0118101993. In this video, I will explain about example 1.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ishraf Izzuddin bin Abdul Razak, B0118101134, prompt to BEKP S1. Today, I gonna explain about example 2.
Assalamualaikum warahmatullahi wabarakatuh. InsyaAllah today I will explain about electric scalar potential. Okay, to start, supposedly we want to move the charge at point A to point B. Okay, so to move the charge, we will need a sufficient amount of force. Okay, to calculate the force, the formula is F equal to QE. So the Q is the magnitude of charge and E is the strength of electrical field, and the unit will be Newton. Okay, and then to find the differential amount of work, okay, we will the formula is negative F dot dl. So the formula we put negative because of okay, the negative is represent the external force needed to move the charge because we are opposing the E. Okay, because of that we will put negative F and dl. dl is the differential length from A to B. So we can substitute here. Okay, and we get the formula of differential work. So to convert differential work to work, we need to integrate both sides. So when we integrate here, we will get negative Q integrate AB electrical field dot dl. Okay, so with this equation, we can find V by dividing with Q. Okay, so the equation will be like this, divide by Q. So we'll cut this, we get this. Okay, so here, okay, first A is the initial point and B is the final point. Okay, so we must put in negative because we are opposing the E. If there is here, the sign here is positive, that means the work is being done by the field. Okay, BAB also depend of the path, and BAB is measured in joules per coulomb. Okay, so next, okay, we have an electrical field moving in negative y direction. Okay, so okay, here we have electrical field and Q. So the Q, if you want to move the Q upward, so the formula will be negative because we are opposing the electrical field. But if the Q we want to make it along with electrical field, so the sign will be positive. Okay, so in our case, we want to move the Q opposite the direction of E. So F external will be negative FE. Negative FE because of opposing the electrical field, equal to negative QE. This formula. Okay, so then you want to find the differential amount of work. So also using this formula, F EXT times by dl. So dl is the differential length. So to we can the formula is will be like this, negative. Okay, so to substitute, okay, so first the E is negative. Direction of E is negative Y. So we put here negative Y cap E times by dl. dl is the 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 direction of Q. So our Q is moving upward. So y cap dy. Okay, so final equation we will get like this, Q dot E dy. Okay, then with this formula we also can get differential voltage. Differential voltage equal to differential work times by Q. Yes. Okay, so this dw Q dot E dy over Q, so we can cut off and we get E dy, and unit is joule per coulomb or volt. Okay, itu ah. Okay. Because of R and infinity, so the formula is V equal to negative integrate infinity to R as per at E dot dl. Okay. Because of this is a point charge, so we need to use spherical coordinate system. So our dl will be r cap dr. So if we put all of the thing here and we derive, and at last we will get the voltage at infinity, at the infinity, and R will be Q over 4 pi epsilon R. Okay, in field, if reference potential point is at infinity, so the voltage will be 0 volt. Okay, if Q is not located at the origin, in this case we might have some vector of R that represent the direction or distance of charge from the origin. So to find the potential difference, we can use this expression or this formula. Okay, for n discrete point of charge, so we can use this formula to find the voltage difference, potential difference. Okay, for continuous charge densities, so we need to know the charge represent what. For if the charge represent by its line charge density, we will use this formula. If it's represent by surface charge density, we will use this formula. And if it's represent volume charge density, we will use this formula.
Assalamualaikum and hello. It's my turn Raja to explain example 1. In example 1, 2-point charge negative 4 microcoulomb and 5 microcoulomb are located at coordinate 2, negative 1, 3 and 0, 4, negative 2 respectively. We have to find the potential at coordinate 1, 0, 1 assuming 0 potential at infinity. So the solution for example 1, first we let Q1 equal to negative 4 microcoulomb, Q2 equal to 5 microcoulomb, and we will be using point charge formula V R bracket equal to 1 over 4 pi epsilon naught times QK over R minus RK, which K is number of turn. So substitute Q1 and Q2 into this equation, we will get V R bracket equal to Q1 over 4 pi epsilon naught magnitude of R1 plus Q0 Q2 equal to over 4 pi epsilon naught magnitude of R2 plus C0. We got equation 1. And in this equation 1, we will neglect C0 because assuming that V infinity at infinity equal to 0, so C naught is equal to 0. So we will have to find magnitude of R for Q1 and Q2 by using the respective formula in line 1 and line 2. So we will get magnitude of R for Q1 is equal to 6, magnitude of R for Q2 equal to 26. So we will substitute the value we calculated above into equation 1. We got this line 3 by 6, 26 and epsilon naught. So we got this equation at line 3. By solving the equation in line 3, we will got equation at line 4 by factorizing the equation at line 3. So solving line 4, we will got equation at line 5, which is 9 times 10 power of 3 bracket negative 1.3633 plus 0.9806. So we get the final answer negative 5.872 kilovolt. So in this example, we conclude that at V coordinate 101, the potential is negative 5.872 kilovolt. That's all. Thank you.
Example 2. A point charge 5 nanocoulomb is located at negative 340 while line y equals to 1, z equal to 1 carries uniform charge 2 nanocoulomb per meter. If V equals to 0 volt at origin, find V at coordinate A. B. If V equals to 100 volt at coordinate B, find V at coordinate C. C. If V equals to negative 5 volt at origin, find VBC. Okay, for the solution, first we need to let the potential at any point be V equals to VQ plus VL, where VQ and VL are the contribution to V at that point due to the point charge and the line charge respectively. For the point charge, VQ equals to negative integral vector E dot dl equals to negative integral Q over 4 pi epsilon naught R2 R squared AR at dr AR equals to Q over 4 pi epsilon naught R plus C1. This is point charge. For the infinite line charge VL, negative integral E dot dl equals to negative rho L over 2 pi epsilon naught rho A rho dot D rho A rho equals to negative rho L over 2 pi epsilon naught ln rho plus C2. Okay, so we will get V from the first equation, V plus VQ plus VL, and we substitute from the point charge equation and infinite line charge equation into the first equation. So V equals to negative rho L over 2 pi epsilon naught ln rho plus Q over 4 pi epsilon naught R plus C, where C equals to C1 plus C2 is constant, rho is a perpendicular distance from y equals to 1 and z equals to 1 to the field point. R distance from point charge to the field point. For question B, if V equals to 100 volt at B 1 to 1 and V at C negative 2, 5, 3, we apply the same equation as before because it's same question. We have different value. So rho B equals to 1, RB square root 21, R rho C square root 20, RC square root 11. So we apply the same equation. VC minus VB equals to negative rho L over 2 pi epsilon naught ln rho C over rho B plus Q over 4 pi rho naught epsilon naught 1 over RC minus 1 over RB. VC, and then we substitute all the variable, and then we solve it and we get VC equals to 49.825 volt. And lastly, for the final question, to find the potential difference between 2 points, we don't need a potential reference if a common reference is assumed. So we just use VBC equals to VC minus VB. We have the value of VC and then we have value of VB. So we just substitute it and we solve it, and then we get negative 50.175 volt, same in the question here. So that's all. Thank you.